Okay, so welcome everyone for the second lecture. Today I'm going to talk about, well, I'm going to make the statement of resolution of singularities, and I will talk about some applications to quasianalytic sets. So I want to start. The beginning of the first part is going to have several definitions, because we want to get the full statement of the theorem. I won't prove the theorems of resolution of singularities today. Well, I will give a proof of the local version later on the course. And afterwards, I'm going to talk mostly about applications to like uniformization theorems and their consequences. And in there, I'm going to do the proofs. Okay, so this is kind of the plan. So I will start by talking about a property that I feel like it's important to understand the difficulty of working with quasianalytic classes, which is actually the failure of Weister's preparation. So let me start here by Weister's properties. So a class of functions C is said to satisfy the Weister's property if whenever we take a function, if for all functions, let's say germs at 0 are 0, so I'm going to write like this: germs is 0, 0 belongs to Rn. Could do it with A here. If we know that there exists a D in N, well, maybe I'm going to write in slightly different ways than what I did in the note. Might be clearer. If we know that if we take, say, the first entry and then all of the other entries, so this is in Rn, and all of the other entries, and this is not equivalent to 0. So in particular, at 0, it's not going to be equal to 0. Then there exists a D in the natural numbers and functions, at least function germs. So I'm going to call it C. Oops, I made a mistake. I'm not talking about quasianalytic classes. I'm talking about classes for now, which is there. And let's say Fi for I equals to 0 up until D minus 1, such that the function f of x is given by c of x times now a polynomial with coefficients given by fi, so x1 to the power d plus, and what I didn't say there is that each one of these fi's only depends on the variables x2 to the xn, one to the power I going from 0 to d minus 1, and C of 0 in this case is not 0, so it's a unit. So it means that apart from a unit, apart from maybe taking a very small open set of 0, we can write it just as a polynomial with coefficients in the same class. Okay, this is the Weister's property. So we do know that in the analytic case, it's valid. So in the analytic case, there is the Weister's property. Satisfy the Weister's property. This is my Weister's preparation theorem. And we also know that if say infinity also satisfy the Weister's property, and this is Lagrange preparation. So later on in the course, I'm going to talk more about kind of the heuristic of why it works in this class, but it does not hold for quasianalytic classes in general. So here the theorem that I'm just going to cite from RP, Brzezinski first, no? Brzezinski and Philippe in 2013 is that if Q is a quasi-analytic class satisfying the Weierstrass property, then Q are the analytic class. So there's no other example for quasi-analytic classes besides the analytic ones, which admit the Weierstrass preparation. And one thing that you might recall is that, so later on, I'm going to give an heuristic about why it holds in these classes, but it does not in here. But for now, I'm just going to use the theorem as it is, just to cite one of the issues that we're going to find out, and one open problem here. So if you recall how
yep. Sorry, do you want to assume in your formulation of the Weierstrass property that these coefficients Fi vanish at 0?
Oh, I do. Thanks. For I equals to 0 to d minus 1. Thanks. I do want that. So a question here. Before making the question, let me just fix annotation. Let A be a point, say, in Rn. We denote by QMA the germs of quasi-analytic functions in Q at A. And then the question, we can if Qi Noetherian. So recall that a local ring like this, so this is going to be a local ring, so our local ring, commutative local ring, well, not even commutative, just local ring is Noetherian if every ideal admits a finite set of generators. Now this is quite...
Sorry, André, before you go much further, I just wanted to ask you, the fact that the Fi vanish at 0, I see that you can make a choice of D such that it's true, right? But you can also pick another D, like if you have a polynomial, a pure polynomial in X1, then you don't necessarily have this, right? So like this, you prefer that the Fi vanish at the origin? Somehow?
Yeah, I'm just asking, like, for the property itself, I'm just going to ask that this D is minimal in that sense, right? So this would be equivalent to having this Fi equals to 0. Because
you would want this in the sequel, you will use the fact that the Fi vanish at the origin, or that D is minimal. Or...
Like, I'm not going to use explicitly right now, but it's a useful property, yes. But it's just, I'm not going to use it explicitly now. I just wanted to, yeah.
Okay, thanks.
Actually, like, I don't think I'm going to use explicitly anything related to the Weierstrass property. It's more a comment about what doesn't work, and therefore that this is a question here. If the ideals, if the local ideals are Noetherian. So in particular, being finite generator is something that is not given for a quasi-analytic class. So this is an open question. Quite interesting to know the answer. And therefore, there's going to be several little difficulties that will appear later on when we started talking about the algebraic case related to the fact that we do not know if it's Noetherian or not. Okay. So now that I started with this, I wanted to kind of set up some of the objects that are going to appear in later on for the statement of resolution of singularities. And I wanted to start by defining what a blowing up is, but somehow I wanted to be clear about what is the objective here. The objective is almost completely to maybe recall for those that are not completely familiar, and to set notation. But I don't think that if you ever saw the blowing ups in your life, then it might not be a full presentation. It's more to fix notation, and to give you, if you have never seen it, material to go to search after it, because it is going to be the building blocks of the resolution of singularities. So maybe just before setting everything, I just want to say that M for us is going to be, so we're going to fix, actually, we start with, we fix Q a quasianalytic class. M a quasianalytic manifold, which we can understand in the usual way. So it's a manifold, it's an infinity manifold, where the atlas here is going to be in the quasianalytic class. The transition maps, everything are going to be quasianalytic. The function field that we're going to consider over it is going to be quasianalytic, and manifold is going to be smooth. And just as before, Q of A is the ring of germs at A. Okay, so we start with the notion of blowing up. Well, all of the blowing ups that we're going to do are going to be with smooth centers. So this is going to be kind of given. Now let's just start in Rn so that we review also the way that we usually set the charts of it. So we start by taking n equals to Rn. This is our first case. And we with coordinates. X equals to x1, xn, and C, which is going to be this, what we call the center of blowing up. I'm going to write it in a second. It's going to be what I'm going to use as zero locus of x1, xt. So this is just the set when they are all given by zeros. We're going to see why this notation a little bit later on. Is the center. And the blowing up map with center is the projection from M tilde, which is something contained in our n times projected space in our t minus 1 into our n, where M tilde is equal to the pairs xi, y in our n times the projected space. Are here such that xi yj is equal to yi xj for 1 smaller or equal to I, j smaller or equal to t. And maybe I should say here where the y's are coordinates of this projective space. Took the wrong one. I again took the wrong one. Okay, it's not allowing me to erase for some reason. I'm gonna keep it there. The M tilde is going to be the blown up face. The C is the center. And we're going to give the name for this. The pre-image of the center is what we're calling the exceptional divisor. So the idea, if one wants, is that for every one of the points over the center here, over the line, we're going to replace it by a projective space, the space of all directions passing through it. So the easier way is to think of this. The easier example is in n equals to 2, and with center given by the z x1, x2. So we are blowing up the point in R2. And we are replacing the point by a P1. And what we're doing is that every one of the directions, every one of the different directions that are coming here, they're going to be taken for different values. Oops, this is a different color. That's not what I wanted. Are going to be given by different directions. So we are just separating all of the possible directions of R2 in this case. Now, something that is going to play a role later on is the notion of the charts that we're going to consider. And now this is going to give us, so we have this construction, maybe a couple of remarks. This is a nice projection outside of the fiber E. We call it exceptional divisor because outside of E, this application is an isomorphism. The application from M tilde to Rn is going to be an isomorphism. And it's also going to be a proper mapping. So I'm going to give the definition later on, but the proper mapping is going to play an important role for us later on, as we're going to see in applications. So comment about when I change colors, there is problems. The directional charts. So we make over, so it's a projective space, so we make over M tilde by T charts, or more, but T local charts of the following form. So UK contain M tilde, where UK is going to be isomorphic here to Rn. With coordinate systems. I'm going to note like this. U are noted like this. Maybe confusion there also. K minus 1, dk plus 1, again, such that in this coordinate system, what we want to say is that we can relate the original coordinates, which were an x coordinate, with the new one, and now the u is going to play the role, u equals 0 plays the role of the exceptional divisors, and all of these vi's here, 1, 2k minus 1, then xk is just going to be equal to u, and all of the others, xj, are just going to be equal to vj, for j equals to k plus 1 to n. So the idea of this, we call it the chart here, so the application, the map Let me write like sigma k, which goes from uk to the Rm, is the composition of sigma, the blowing up, with a local immersion. Let's call it yk from uk to m. And in particular, this application here is the first example. As we're going to see, there's going to be others, but the composition of a blowing up with a local immersion, this is what we call a local blowing up. Sigma k is a local blowing up. So just one thing, if we want to, the idea here is that we're covering this projective space, which a priori, let's say that we blow it up R2 again, and we're covering it by two charts. So one chart which exclude a point, so it's going to be in the U1 chart, we're going to have a point which is 0 and a point which is infinity, which we are not seeing. So we're covering all other points. And in the other chart, unable to change it. We're going to have 2 points that are going to correspond to the 0 and plus infinity of the U2 chart. Sorry, what did I do? I think I'm so confused about the fact that I was not able to change colors. I wrote something that has no sense. Now this is going to play the role of plus infinity in the U2 chart. And this is going to play the role of 0 in the U2 chart. So like this, we cover the projective space by k local coordinates, and each one of them is going to be what we're going to call later on by local blowings up. Now just comment, it's going to be a comment because I'm not going to prove anything here. Blowing up in general, or general, sorry. No, in general manifolds. Manifolds. So we are always going to be able to blow up a center which is in the class, so a subvariety, a sub-manifold, sorry, of the class, of the manifold. So let's just start by saying that a Q submanifold C of M is an embedded submanifold such that for every A, there is a neighborhood U of A and functions F1, FD. Can I do this? Okay, it's allowing me to do this again. F1, FD, which are in a Q of U of A, such that, of course, C is going to be the 0 locus of these functions. So I'll write once again. C inter U of A FD equals 0. And the Jacobian of F1 FT is invertible So maximal rank. Of maximal rank in U of A. So in particular, I recall that we had the inverse function theorem and the implicit function theorem in the class. So we could we closed it by the operation that given by the implicit function theorem and the inverse function theorem. So we can always find local coordinate x equals to x1, xn at A, such that fi is equal to xi for I equals to 1 up until D. So this center that we have here, we can always just look at it as in the first case, right? Of the blowing up in R locally after a change of coordinates, after a Q change of coordinates that is in the class. And then given a general manifold, we can define the blowing up sigma m tilde to m by a center C. A center means Q submanifold of M, essentially by patching. So I'm not going to actually give the definition. So I'm going to do this by patching together the local definitions that are the local constructors. So if you want to see the details, you can find the paper of Bierstone-Millman. 2004. We will have as a paper. Maybe I should put at least the journal, because there are more than one paper here. It's paper published in Select. Yeah. So it is possible to define what a global blowing up is in the full generality in M, but we can keep the idea that we're covering by this kind of charts, very simple algebraic charts, and that we are mostly working at our end up to making a change of coordinates. Kind of the idea. Now, one thing that I wanted to say connected to this is that the pre-image here, the E, given by the pre-image of the center, is again the exceptional divisor of the map. And we call it the exceptional divisor even if we blow up a center, which is actually a hypersurface. So this is not maybe compatible with what is the definition of an exceptional divisor in algebraic geometry, which is the set, well, basically the set where it's not local isomorphism. In this case, it's going to, even if the set is a if the set is a hypersurface, then the blowing up is actually an isomorphism everywhere. But it is arguably the right way to deal with in a resolution of singularities, to even call in this case E as exceptional locus. This is just a convention. And this brings me to talk about simple normal crossing divisors. So E is the exceptional divisor, and we want to keep track when we do more than one blowing up of all of the divisors that are going to appear. So a simple normal crossing divisor. E is an ordered collection. E1 to E, a finite order collection, such that, or where these EIs are irreducible smooth divisor. So at least for now, since we didn't define what irreducible, what ideal sheaves are going to be, we can just think as a Q sub at hypersurfaces. With the notation that we just used before, so sub manifold connected of dimension -1. And if we take all of them, they are normal crossings. So that is, for every A in E, there exist coordinate systems UV, U1, UR, V1, Vs, such that all of these guys are given by the zero locus of the product of the UIs. 1, 2R. Just do like this. So when all of them are equal to 0. This is essentially what we're going to do. And then there's a notion of, in order to make things compatible with the exceptional divisor. So there we define what a blowing up is. So a blowing up, so given, I will need more space. Blowing up is compatible with a simple normal crossing divisor if the center union with E has normal crossings. I'm not going to note exactly what it means, but so maybe I can again just say without putting everything again in the coordinate systems, that is, for every IA in E coordinate systems there exists, just as before, coordinate UV such that the center now, besides this information, is going to be given by some of the U's. Let me put R prime and some of the V's. So essentially what you want to consider here is the situation that you have some transverse crossing between the center and the exceptional locus, so it can be a curve like this that is cutting transversely. The situation you want to exclude the situation that you have a tangency. Not normal crossings. Normal crossings. At least for the centers here. So we say that it's compatible with E.
Sorry, André?
Yes.
Yes. So in this equation defining the center, is it the same R prime for U and V?
No.
Okay.
Sorry. And I think
Sorry, I also have a small question.
yeah,
Maybe thank you. Maybe I misunderstand the definition, but C and E are in M basically, right?
yes.
So the way it's written, it has nothing to do with the sigma. I don't really understand.
Wait,
Like you just wrote that.
Yeah,
means,
I'm just saying that. So the blowing up is with center C. I didn't say that.
right. Okay. So just you have a divisor on M, you have the center C, and just if the divisor and E have this relationship, then any blow up with center C is compatible with E. That's what it means, right?
It means that any blowing up with a center with this condition. So in this case, for example, in the case in the left, it's going to be compatible. But in the case in the right, it's going to be not compatible. So you cannot blow up a center. Yeah.
Yeah. Thank you.
So the remark here is that if sigma from M tilde to M is compatible with E, simple normal crossing divisor in M, then the exceptional divisor given by the prime image of E union with the prime image of C is also simple normal crossings. So in this setting, we are going to use, and we will use the notation sigma from M tilde E tilde to M E. Notation that we're going to use. Okay. So now after this this first part of the introduction, I just wanted to make an example of blowing up and a first example of a resolution, not exactly of a resolution of singularities, but a nice example of a blowing up of a surface that is actually going to play a role in the second part of the course, today's course. And this is going to be an example of Birch-Newman. So here is just the comment that we can maintain this couple by blowing up the centers which are not tangent to the exceptional divisor. Like this. So the example that I want to give you is an example from Birch-Newman. I think it's 98, which we're going to come back to it later on. And we're going to consider here the function f. So m here is going to be R3. And the function f of x, y, z is going to be given by z to the third minus x squared yz minus x4, and x is going to be the set of zeros of f. And the idea is to study this set via the blowing up. This is the idea. So the first thing I want to note is where this set is not going to be, at least a priori, it's not going to be a hypersurface. So it's enough for us to consider the gradient of f. If the gradient is non-zero, then we know that it's a hypersurface. So the gradient of it is going to give us, well, minus 2x, y, z, minus 4, x3, minus x2, z, and then 3z2 minus x2, y. And from this part here, we know that the gradient is going to be 0, so gradient is 0. If and only if, well, first of all, xz is equal to 0. And from the second part, sorry, not if and only if. We know that 1 that 2 implies that xz has to be 0, and 1 therefore is going to imply that, well, if x is equal to 0, sorry, if z is equal to 0, if x is equal to 0, then by 3, z is equal to 0. And if z is equal to 0, then by 1, x is equal to 0. So we take from this that the curve of singularities of f, or better, the curve of points where the gradient is not 0. So gradient of f equals to 0 is going to be given by x equals z equals 0. So this is the natural center for us to blow up. So we consider C as the 0 locus of xz, and we will make the blowing up. Make a blowing up. Sigma with center C. So we have two charts to consider. I will first consider here the chart, which is the interesting one. The interesting one is the X. So let's consider the X chart. So the X chart was that one that X would become an exceptional divisor. So in here, the way that we're going to notice X is going to become the U. I will keep the notation Y since we didn't touch Y. And Z now is going to become of the form U times V. So in this situation, when we make this, then the composition of F with sigma is now going to become U to the power 3 V to the power 3 minus Y V minus U. And I want to just make an interpretation of what is going on here, following this, the set that is going to be given by the 0 locus of this part. So here is the exceptional divisor, is what we accumulated as a monomial there, and here's the rest of it, right? So we have a situation, we have an axis Y, and if we take a Y, which is, so which one is the easier to do for? Yeah, let's do. If we take Y, which is bigger than 0, then we have this equation here, E3 minus YV minus U equal to 0 with a fixed Y, and therefore we get that U is going to be given by V third minus Y times Z. And this guy has 3 real solutions. It has V minus the square root of Y, and V plus the square root. Sorry, did I take the right one? With the plus. Yeah, that's correct. Minus, plus the square root of Y. So if we take a positive V here, what is going on is that I'm going to make here a little plane which corresponds to fixing y equals 0. There's going to be the u equals 0 given here, and then the rest is going to be, well, it's a polynomial with 3 solutions. So let me see if I can change the color. Cannot. So it's going to be polynomial like this. On the other hand, if we take a y which is negative, we do again this game, u equals 0. So here was a positive y, and here is a negative y. Then if we do the same game, now the difference is that we're not going to be able to take this square root. So we're going to have 2 of them, which are going to be imaginary. So what we're going to see is simply, well, a hard time drawing this. Oops. Just a cubic, but a cubic changing direction like this. We're going to have something smooth like this cutting. So there's going to be a difference in how we're going to see. So we're going to have this exceptional divisor there and how the set is going to work. So y equals 0 is actually a special point. It's a special point where we have tangency between the, so we see that now we have something which has gradient everywhere, different from 0. But there's going to have some tangency between the variety now given by this part here equals to 0. Let me just move like this, and the exceptional divisor equals 0. So I'm not going to worry about this for now. I'm just going to not draw, but just make an interpretation of what is going on here. It means that for y bigger than 0, certainly there is a singular point of the set before blowing up, because these 3 points are going to be joined into one. But the point that is here is less clear, right? Like indeed, if y is smaller than 0, then v3 minus yv minus u satisfy the hypothesis of the implicit function theorem. In respect to v. So this means there is a solution the form v equals to g of u and y locally at the point y bigger than 0 that we chosen at this point here. Let's give it a name, b. And moreover, by the implicit, still with the property coming from the equation itself, and g of 0y is equal to 0. So what I'm making this comment? I'm making this comment because now if we take z equals, since g of 0y is equal to 0, we can write it as x times the tilde of xy. And therefore we can take z equals to g tilde of u y is a function we take here the function h given by z minus g tilde of uy, such that the composition with the blowing up is going to be exactly, well, not exactly, because there's going to be u, u times v minus g of uy. So what we are saying is that the set x that we have blown it up and we saw here, the set a priori is locally given over this point as something that is smooth, is given by z minus this g tilde. So after blowing up, we're going to have this complicated set. We are going to have the point 0, and all of the points where y is actually smaller than 0, the set is going to be smooth. While for points which are actually bigger than 0, then the set actually is going to have these three lines, this cubic that is going to contract to a point. So actually, you're going to have a situation like this. Oops, this is not exactly one. Like this. So this part here is going to be smooth, and that part is not going to be smooth. So I'm going to keep this example for later on, because it's an example where the algebraic structure that is coming from the f equals 0, it does not capture the points where the set is not smooth. And this we can see it after blowing up. So we made it blowing up, we made the interpretation of what happened after blowing up. We've seen that it's being smooth for y smaller than 0, and moreover, that it can be blown down for something which is smooth before the blowing up. Keep this example in mind. Further on. So this example is going to play a role in what I'm going to start talking now, which is the notion of ideal sheaves and the notion of privileged ideal sheaf. So let me give you a couple of definitions. The first one is...
So, Andres,
sorry.
I'm sorry to slow you down a little, but
no, go ahead.
I'm not sure about the morale of the story you just told us. Are you telling us that the set at y negative was smooth to begin with?
Yeah, that's what I'm saying.
Even and why did we do all of this? Because it wasn't clear from the equation, it wasn't clear from the gradients.
Exactly. So if you take the gradient, yeah, that's the morale indeed. So if you take the gradient, we're going to see that what we get is x equals z equals 0. So these are the points where f is of order 2.
So this is the candidates for this. So those are the candidates for the singularity, but we are not sure that they are singular points.
Of the set, no, because the set it might admit another local equation where it's a hypersurface. And then we made the blowing up, and we verify that over the points where y is smaller than 0, then we do have local coordinates that do give us something which is smooth. So
this is really real geometry. Okay.
Right. So this is what
I never had to wonder about such questions until now, because the gradient was enough. But okay, I see now that okay.
Yeah. So that's the moral. So I'm going to keep. This is going to be a good example to see some of the pathologies that can occur in the real case.
Okay. Thanks.
So to give the definition of what we're going to talk about now. Set. A set X in M is a Q set, so quasianalytic set, if for every point A in X, there exists a neighborhood U of A such endouts and functions. And a collection. F alpha, where alpha in some index set A of Q functions in this open set, such that the intersection of X with this neighborhood is given by the 0 locus of this collection. No, this is enough. So this is what we're going to mean by a Q set. Now, since we have this idea of passing through a collection of functions, it is natural to work with the notion of ideals. So we consider from now on ideal sheaves I over M, that is a given for every open set U of M of an ideal YU of Q of U. We specify all the sheaf conditions, so gluing, restriction, etc. And we're going to denote the germs of I at A. And without giving I made an example. So without taking much longer, I just want to give you the property that we're going to study in the next 10 to 15 minutes, which is the following: an ideal sheaf I is privileged if for every A in M, there exists a neighborhood U of A such that and the ideal over U admits a collection is generated by a collection of functions globally defined in U. And this implies that for every B, let's do the opposite. Here. Why not be able to change? Like this. Then yeah. The germs at B are just going to be given by all of these functions F alpha, their germ at B for all alpha in this A and for all B in the open set. So it means that you actually have functions which generate over the open set all of the germs of this open set. So this is what we're going to call privileged. If the rings are Noetherian, so in the case of an analytic, we normally don't talk about privilege, we talk directly about finite type ideals, because then this index set that we're taking here, because A is to make it compatible as before, the index set is going to be finite. But here we're not asking anything about this index set. It's just going to be, yeah, just an index set. We're just asking actually, the only thing that we're asking is that these functions are global over U. Okay. And in this case, if you have a privileged ideal sheaf, then you can define the zero locus. And the zero locus of a privileged ideal which are going to be simply the points A in M such that f of A equals to 0 for all f in I of A is a Q set. So in this case, it becomes clear because for every point, you're going to have an open set, and then you have this collection, and therefore we have that this set given by the zero locus is actually going to be a Q set, almost by definition. By definition. But this is actually normally is going to be actually a necessary condition for it to be a Q set. So let's see a couple of examples. Well, we're going to see that locally it's not going to be the case.
Can you raise can you lower the board for just a second? Okay, thank you. Just for the remark.
Yeah, sure. Okay, so I'm going to put it like this. So let's make a couple of examples of non-privileged sets, or at least, sorry. Give me a second remark first to build up, because we would like to have, so we have in one direction, if the ideal is privileged, then we have a Q set, and we would like to attach to every Q set an ideal. And if we can, something which is privileged itself. So here there's an idea. Where is it? Yeah. The second remark is given a Q set X, we may consider the structure sheaf. Which we're going to call I of X given by, so the germs of it are simply going to be all of the functions such that these functions are zero over the set. So given a Q set, we may consider this ideal sheaf here. Now I want to argue with you that this is not, in the complex geometry case, this is going to be a coherent ideal sheaf, in particular privileged, but in the set that we are here, it's not going to give us something which is privileged usually. And there are two examples that we can see that. The first one is the Whitney umbrella. There are more than two examples, but two simple ones. X squared minus z minus the square. And in here, this function f is irreducible. We cannot do it better than here. So the ideal sheaf, the structural ideal sheaf at 0 is going to be given by this f. But if we take some point here with z0 is smaller than 0, then the ideal sheaf at this point, the structural ideal sheaf at this point, is actually going to be given by x and y. It's actually given by x squared minus y plus y squared. Sorry, so here I would like that to be negative, yes. So that this becomes x squared plus y squared. So it's actually going to be given by x and y. So we see that at every point that z is smaller than 0, we need two functions to generate the ideal, but at z equals to 0, we only have one function. So this is the case that there's not going to be an open set around 0 where I can generate all of the points in this part of the set with just the function f. We will not be able to generate x nor y with this construction with just the function f. So Ex is not privileged. And example 2, because this example might tell you that, okay, so there's a change of dimension. So this might make a difference. But if we take the Pearson and Newman example, well, let me just go out. I of x is also not coherent, is not privileged. because I recall that we had this strange kind of looking surface that in one part of it right, had this form, and in the other part was smooth. And we had the function f here equals 0, but at this point, it was smooth. But the gradient was equal to 0. So at this point that are here, so ix at 0 was generated by f, which was irreducible. But if we took I0, Y0, 0 with I0 negative, this was given by that V minus G tilde, yes, of x, y, which are not the same functions. So it's not privileged neither. And this is going to play a role a little bit later, once again. Okay, so the structural sheaf is not necessarily like which is coming in complex geometry. It works very, very well because of Theorem of Loca. But in this case here, it's not working so well. So we can actually ask for something a little bit less. We don't need maximality. We don't need to take all of the functions which are 0 of the set. We just need some functions which are 0 of their set. So the question for the next couple of moments is, for every Q set X, is it possible to find a privileged ideal sheaf I such that C of I is equal to X. So not necessarily the structure ideal, not necessarily this one. This we saw that it's not possible. But for example, for the Whitney umbrella, we can, at least locally, right? We can just take the ideal generated by F in this open set. It's not going to be the structural ideal at this point, but it works perfectly fine as just an unprivileged ideal sheaf, because if you just take the ideal sheaf where at every point it's just the function f, this is going to be privileged. The same way, in the second example, if we just take the function f and we take the ideal sheaf generated by f at every point, this again is going to be privileged just by the definition, because for the open set, I just have this function defined globally, which generates the ideal at every point. So this leads to this question, and the previous remark that we just did for these two examples is that locally you can always. So locally it's possible. So yes, so locally, yes. Because if you take the definition again of what is going to be a Q set for every point, we might take the neighborhood and we might consider the ideal given by all of these functions fi, f alpha defined on this neighborhood. So we're going to find a neighborhood and an ideal sheaf defined on that neighborhood given by global functions, which we have this property. And therefore, it's going to be privileged at that open neighborhood by definition. Almost by definition, yeah, by construction. Why did it locally? Not full figure. Having issues with my software that yeah. But globally, the answer is no. So there are some very nice examples of Cartan here that go back to Cartan. which are global in Rn. So I just want to cite, if you're interested in these kind of examples, several of them in a book of from 1966, Introduction to the Theory of Analytic Spaces. And these are very nice examples because they are globally defined on Rn. It's even compact in Rn. There's examples of that. There's examples of several pathologies. But when I was preparing the talk today, they are not completely clear that they are not privileged at a first regard, and it's necessary to use some lemmas to prove it. So instead of doing these examples, I'm going to give you just an idea of an example which is going to be over an abstract manifold, in the sense that we're going to glue the two charts. So it's not going to be something which is in Rn a priori. So that's the disadvantage compared to the example that are coming from here. But on the other hand, it's going to be easy to see that it's cannot be privileged, right? So the idea is to, so I'm just going to give the idea. So the idea is to glue the example of Bierstein and Millman. So we'll do again the drawing. So we have this Y here, and we have the part right, becomes a smooth later on. We're going to glue this example coming from Bierstein and Millman with another chart. See if I can do this. I wanted to use colors. So I'm going to take some open set sufficiently small in RD, and we're going to glue it. Oh, wow. It makes a big difference. With another one, some open set U1 with another set U2, and we're going to glue it by a rule that over the gluing part, we're just going to take Z tilde equals to that Z minus G of XY. So now the set X equals to 0 in the new chart is just going to be Z tilde equals to 0. So we're able to do that because in this chart we have this way to transform it. And the other coordinates, we're going to take just X tilde equals to X minus sine of 1 over Y minus delta, and Y tilde equals to Y. In such a way that this delta is sufficiently big so that the transition is analytic. Delta big, so that the transition analytic. But now the remark that we can make is that the curve given by the order 2 locus of F is something that depends on the algebraic structure that we have given. So if we take the ideal sheaf generated by F here, and we say, okay, we're just going to extend it to the left part, to the blue part, then the curve given by X equals Z equals 0 needs to be continued. It's going to admit an analytic continuation to the other part. And in here, the thing that might happen, or that is going to happen, is that the curve that is, of course, no, it didn't work. Why is it not working today? Okay, there's something going on in my, okay. The point is that after this transition, the curve that was completely smooth, after it's going to be a sinoid of 1 over X, and choosing delta we're going to get that it's transcendent. So we're not going to be able to extend the ideal sheaf given by f equals 0 in the first chart to the second chart in a way that doesn't that is not transcendental. So this set here is going to give you something that globally, so locally it will admit, because locally it's just set tilde equals 0. And in the other chart it's just f equals 0. But globally, we're not going to be able to have privileged ideal sheaf that gives us the set. Okay.
In the polynomial setting, in the polynomial algebraic setting, so are all ideals privileged or not?
In the algebraic case, normally,
No? Yes.
yeah, you can always make it in.
Okay. Okay.
Yeah, they're finite type. Yeah.
Yeah. Okay.
Usually people even work in the projective space directly, so that then yeah.
Yeah. Okay.
Yes. Okay, so let's now get to the first statement, almost to the first statement. Now I just want to make all of the things that we said, the last parts of what we said, the definitions of what we want to obtain. So putting everything together. So now given last definitions before we start proving things. Well, before we state a theorem, then we start proving things later on. So given a blowing up, and a privileged ideal sheaf I in M, the total transform I'm going to call it like this for notation purposes, is the ideal sheaf whose talk given by is generated, well, like this, generate by f composed with sigma for all f whose talk at a point at B is generated by for all functions f in the ideal of sigma of B. So just the pullback. You pull back all of the functions that were in the image of that point B that we're considering. And our objective was always to make these functions become monomial. So given M and a simple normal crossing divisor E in M, I is monomial if for every point there exists a neighborhood such that this coordinate system, mixing up the two parts of what I'm writing. Oh no, coordinate system be adapted to E such that the ideal IA is just given by U alpha. That means U1 alpha 1, UN alpha n, sorry, alpha R, where the alpha belongs to the multi-index here. This is what is going to be 100. So now with all of the results that with all of the definitions. So,
sorry once again, Andre.
Yeah, go ahead.
In the previous definition of the total transform, I have a hard time understanding who lives where.
So with this talk at B in M tilde is generated by.
Okay, I thought B was in M. Okay.
Yes.
Okay.
Yes. Sorry about that. Yeah.
No, it's
so that we send it down. So now this is the objective. When I talked about the rough statement of resolution of singularities, our objective was always to pull back an ideal so that it would become not an ideal. We started with just a function, so that it would become one only. So now we are ready to make the statement, which I'm going to do in the next part, so that we have a complete statement in just one page of the global resolution of singularities in this case. The theorem from here from here to the yellow. Actually, yeah, let's let credit where credit is due. Also, so 2004, and Bircham plus Valette in 2013. That's when they found the formulation with the privileged and not finite type. So the following. So let's do the complete thing. Let M be a key manifold. E a simple normal crossing divisor. And I a privileged ideal sheaf. Now there's a technicality when we work outside of the algebraic category that we should restrict ourselves to relatively compacts. So we're going to say that. So for every relatively compact open set, M0 of M, let E0 be the E intersected with M0, I0 be, the ideal sheaf at M0, the restricted ideal sheaf at M0. And now the statement is there exists a sequence of compatible E-compatible blowings up. MT minus 1, ET minus 1, up until M0 is 0, such that if we denote by sigma decomposition, so here is going to be sigma 1 composed with sigma t. The pullback of I is monomial. And just a quick example of why we need to restrict to relatively compact sets. It's going to be more or less clear. If we take the ideal I in R2, given by y squared minus sine of x squared, then this ideal, you cannot monomialize it by a finite number of at least connected center with connected, it blows up with connected centers. So it's going to be quite simple to principalize. It's just going to be this the finite function several times. So in this case, you're going to need to restrict to compact sets so that you have a finite number of lines up. Else, we can. It is still possible to get to give a. It's possible to give a statement which is global, and we're going to talk about this later on. But it's almost enough to restrict for the purposes of a relatively compact at this time. Yeah. So this is the first statement. And here I just want to note that the privilege assumption here is what brings up the valence to the theorem with Peterson and Newman. So in the first part here, the ideal sheaf was supposed to be a finite type, such as in the algebraic and analytic case, but it can be done in the privileged case also, as they remarked in 2013. Now that we've seen the global version of the theorem, I actually want to talk a little bit about the local version. So there was 3 techniques that we wanted to talk about. This is the first one. And I actually want to state the second one before I start making applications. So I think that the goal is going to make actually to state the second one. And so this is finishing this part, and I'm going to now start talking about local resolution. Which is going to be more adapted to when we talk about sets, and especially to Q subanalytic sets, as we're going to see. Exactly because we cannot always assume that things are privileged. So here we start by saying what a local blowing up is. We already seen the typical example. So a compatible local blowing up. Now, from U tilde to M, E is the composition of a blowing up with a local immersion. And now proper and say proper. So we need a second definition before defining what is going to be the local resolution, but I anticipate because I see that I won't have time to state everything, and I actually wanted to prove a result today in the last 10 minutes, which is going to be connected with proper and semi-proper. But the local resolution of singularity is basically going to tell us that there exists a sequence of local blowings up, or several sequences of local blowings up, where the pullback of the ideal is going to be monomial, but we need some sort of condition so that we cover all of M. And this is going to be the condition given by this proper and semi-proper morphism. So I recall that a morphism phi of n to m is proper if for every compact set K of M, the preimage of K is compact. And the morphism is semi-proper if for every compact set K in M, there exist compact sets L in N such that phi of L is equal to K. And the idea is really that you are able to cover all of M by compact sets like this. So actually, I won't get to the statement, but the result then that I would like to just give and then discuss in the last part of the talk, the following lemma: let phi from n to m be a semi-proper morphism there exists a generic submersion. Where's the, yeah.
So, sorry, Andre, can I interrupt you again?
Yes, of course.
No. So in your definition of proper and semi-proper morphisms, for you, what is exactly a morphism?
A Q, yeah, that's true. It's just should have said where's the category. It's going to be here a Q morphism. So in the quasianalytic category. So it means we have so these are M and N are going to be Q manifolds. So we have atlas which are Q. So it is enough to say what a Q morphism is at open sets.
Okay.
And an open sets just means that every one of the entries are going to be in the class quasianalytic.
Okay. Thank you.
So there exists a generically submersion in Q such that the composition is proper. So this is the last point that I want to talk about today. So it's just to say that the difference between semi-proper and being proper, you actually you can always compose with a little bit more, which is going to be generically a submersion, as we're going to see. So locally, it's even going to be an isomorphism, and in such a way that the map is going to become proper. Here's M is proper. So the idea here is that we want to transform. So for each one of the Ks, we took the preimage is going to be compact, and now what we know is that we are going to be able to cover with the set L. And the basic part of the construction, so the basic, the main idea is to consider the projection of the sphere I'm going to write it like this. given by xt equals to x, where the Sn is the sphere given by x1 square, xn square plus t square equals to 1. So this map here, this tau tilde, is going to be a generic submersion. Sn is going to be so. Submersion. It's a submersion everywhere outside of the hemispheres of the hemisphere given by t equals 0. Sorry, the other is equal to outside of this is all equal to, yes, t equals to 1. Sorry. And it's a proper, this one is also proper, it's local generic of maximal rank, and it's proper. We are in a closed compact set, is a continuous function, so it's going to be proper. And T tilde of Sn is simply the ball of radius 1 and center 0 in Rn. So the main idea is this one. So what are we going to do? This is going to give us some intuition about what does generically, what does semi-proper means. What we're going to do is that now consider a locally finite cover of M by compact sets. So we cover M by locally compact cover. So by semi-properness, for each alpha, there are finite numbers of connected compact sets L alpha k, kj, d that depends on alpha, such that the image by the mapping of the union of this L alpha j's is equal to k alpha. Now the idea is that we're just going to compose for each one of these L alpha j's with that morphism given by theta tilde. So let me make a hypothesis here just to simplify things. If with actually this can be shown since we're in a metric space without loss of generality. But there's something to prove here. So I'm going to come back to it in a moment. We may suppose that L alpha j is containing some Rn, and there exist coordinate systems such that the L alpha j's are equal to walls of radius 1. So if you have this case here, then for each one of these alpha j's, we're going to compose with this map here. Then for each alpha j, we consider tau of alpha j from Sn to Rn, such that the image of it is equal to L alpha j. We consider, so let me put an index out here. Let n be the union all of them, and theta tilde from n to n be the morphism with restriction to each one of the Sn alpha j's is equal to delta of alpha j's. Now, we claim that this is the morphism that we are searching for. Claim delta bar is the searched morphism. Now, I don't want to spend a little bit much longer, but this actually can be seen in a not too difficult way. You take any compact set, since this is going to be a locally finite covered by M, it's going to be covered by a finite number of these k alphas. And for each one of these k alphas, the prime-image is going to be exactly in a finite number of these L alpha j's. So you're going to have that the prime-image of k is going to be contained in a finite number of this Sn alpha j sets. So since these are compact, and the prime-image of a compact set is going to be a compact, and the prime-image of a compact set is going to be closed, it's also going to be compact. So this is going to show that this now map, the composition of phi with the theta tilde is going to be proper, which is what we wanted to show, which was all of our goal here. Now, the comment that I made here is that without loss of generality, we may suppose that is equal to B1 equals 0. So this is, of course, there is an argument here to be made. So in general, you can only cover it by balls of this form. So we may cover it by the ball of these forms, but then we have to take care of knowing that when we project, once again by phi, we get something that is locally finite, a locally finite compact by, again, compact sets. So then it's convenient to take two locally finite covers by compact sets, one containing the other, and to argue that we can cover the first by balls, which are contained in the second. So there is a little argument to be done here for this star, a topological argument. So I'm going to finish today right now because I already passed a bit the time. So thanks a lot, and sorry for the week. Alors. Yeah. So I finished now. I'm sorry for it.
Thank you.
Thank you, André.
Okay.